So what we'll go through today is more on the greenhouse effect, the natural greenhouse effect. So going through the calculation exercises, looking more closely at that. And then one important thing we'll discuss is how the temperature changes as you move up the atmosphere, and the reason for why the temperature changes as it does, and the importance that has for the greenhouse effect. Let's see. So we'll talk about that. So yesterday we did this very simple model of the Earth without any atmosphere, and it turned out if we didn't have an atmosphere, we would expect the temperature of the Earth to be like around minus 20 degrees. And then we added a simple atmosphere and came to a much higher number. And now for the calculation exercises, you're going to make it a bit more realistic than this completely opaque atmosphere that we used yesterday. So what we'll do is we'll go through the exercises, and then we'll talk a bit about what they say, what we can learn from. So the first exercise was to start just from knowing the temperature of the sun, the surface of the sun, and the radius of the sun and the distance between the sun and the Earth, to go from that to calculate how much solar radiation, what's the energy in the solar radiation that reaches the Earth's surface, and then doing the same thing we did yesterday with calculating the temperature on Earth that results from that, if we assume no atmosphere. So the first thing we want to know is, of course, so we want to know if, like, a square meter on top of the Earth's atmosphere, how much sun on average, or energy from the sun we receive there. Well, a good starting point is to know how much energy does the sun emit, right? And what determines the energy the energy that the sun radiates? What are the main determinants of that? So we know, So we want to calculate the total energy flux from the sun. We know that the sun will send out, so if we assume again that this is a perfect black body, so the emissivity of the sun is 1. Then we have sigma, the Stefan Boltzmann constant, in watts per square meters per Kelvin to the power to 4, right? Times the temperature of the sun, the power to 4. And this is in Kelvin to the power to 4. So this is, what's the unit of this now?
Watts per meter square.
Watts per square meter. So this is the amount of energy that the sun radiates per square meter of its surface. So if we want to get the total energy flux from the sun, we have to multiply it by the surface, the area of the sun, right? So we multiply it by the area of a sphere. So 4 times pi times the radius of the sun raised to 2. And this is in square meters. Okay. So now we have something, so before we had something that was watts per square meters. Now we multiply it by square meters, so we get watts, just watts. So energy per second that leaves the sun in total. Okay. The next trick is then so this is the amount of energy that leaves the sun, right? So how much of that is captured by the Earth? So the way you can think about this is, we have the sun here, a square, and it radiates in all directions. So we can try to estimate the average intensity of the sunlight at some distant point from the sun per square meter. So if what we do is now we have the total energy that leaves the sun. So if we look at the sphere that surrounds the sun at the distance of the Earth, and then we assume that this radiation is spread evenly over that square, then we can calculate at the distance that the Earth is from the sun, how many watts per square meters again is the intensity of the solar radiation at that point. Because this, of course, you spread it out as it moves out through space. It sort of gets more and more dispersed, right?
It's like a big sphere.
Like a big sphere, exactly. So if we want to calculate what you can call the solar constant, I think, in the exercise, if we divide this by the area of a sphere, that is the radius or the distance between the sun and Earth. So times r sun to Earth. P. Does that make sense? So this is the formula for calculating the area of a sphere. So the area of a circle is pi times r to the power to 2, right? And the area of a sphere is 4 times that. So that's just the basic geometric formula for calculating the area of the square. So that's why you have it here to calculate. This is the amount of the intensity of the sunlight per square meters of the sun's surface. And then you multiply it by the total area to get the total radiation that leaves the sun. And then you spread that out over a much bigger square. The square that is where the Earth is in distance from the sun. Okay. Does that make sense? Yeah, it is a ball. So it's a ball, but it's the surface of that ball. So the problem is I can't draw in 3 dimensions, but it's not the circle, it's the sort of the round ball and the area of that ball. So this is for the pi r2 is for the circle, and this is for the sphere.
Yes.
So it's 4 times as big. Yeah.
But there's only some of it facing the sun.
Of the Earth.
Yeah.
Yeah.
And some of it has a strange angle, so there'll be a lot of reflection.
Yeah.
But
So
take that into account.
can we? Yeah, we'll get to that. So let's first. So this will be. So what we're calculating here now is sort of if you take 1 square meter at the distance from the sun, that is at the same distance as the Earth, how much solar radiation do we receive there? And then the next step will be accounting for what you say, Thomas. So if we want to average that out over the whole Earth, what do we get that? So let's just put some numbers in here. So we have Stefan Boltzmann's constant, which is 5.67 times 10 to the power to minus 8, multiplied by the surface temperature of the sun in Kelvin, so about 6,000 degrees Celsius. How do you think we know this? How did we measure the temperature of the sun?
Color of the light or something?
Say again?
The color of the light?
Yeah, probably. Or actually probably doing this in the opposite direction, right? Starting from actually measuring the intensity of the sunlight and then going backwards and saying, looking at how you showed this graphs yesterday of the black body radiation. And given that spectrum, you can calculate through the Stefan Boltzmann's equation the temperature of the object that emits that radiation, if we assume that it is close to a perfect black body. Right. So this is so on the denominator here we have the total energy flux from the sun. And then we want to know, so this is the total energy flux that leaves the surface of the sun, right? But if we want to know how much that is for every square meter at a certain distance from the sun, that spreads out. It goes out in all directions, right? So it spreads out. So if you take a sphere at a certain distance, you can and divide it by the area of that sphere, you get the intensity in watts per square meters again. So I have the distance here, the radius, so the distance from where we have the sun, and at some distance here we have, and this is not in scale, we have the Earth. And here I have r is the distance here. But then we look at the whole sphere because the sun of course radiates in all directions. So times 4 times pi times, and now we have to be careful so we have the right units. So we have 696,000 kilometers. So the power to 6 meters. So we get it in meters, right? Power to 2. And then the distance, sorry. The distance from the sun to the Earth was 149 billion meters, right? So the answer we get is 168 watts per square meter. So that is what you sometimes call the solar constant. So if you measure the solar radiation that flows through 1 square meters at the top of the atmosphere on Earth when it's facing the sun, perpendicular to the sun, then that's 1368 watts per square meters. Exactly. So what would, it's a good question. So the implicit assumption here, as Martin says, is that what leaves the sun reaches the Earth totally unimpeded. There's nothing that absorbs the radiation in between. So what could it be that would, is there something in space that would do that? Well, that could happen, but this astronomy is not my strong subject. But I don't think it happens. So when does this happen? When do we see something blocking us from the sun? And that's when you have a solar eclipse, right? So that's the moon. But otherwise, but it does actually happen. You're right. I know there's been occasions, or a few years back, when one of the planets were passing in front of the sun, right? But it happens very seldom that actually one of the other planets actually pass right in front of here. And when it does, it's like a small speck on the sun. So we can disregard from that. And the space, apart from the other planets, you can treat it as a vacuum. There is not anything there that absorbs the radiation in its path. So, like the old light bulbs, like the old traditional light bulbs, fluorescent light bulbs, usually was somewhere between 25, maybe 15 to 60 watts. So you can think of, but it's excellent because how do you get a grasp of this? So one thing is, maybe some of you will know, when you're going back to the microwave again, that's good for lunch, you can sometimes turn the dial and have different effects on the microwave. So if you have a strong microwave, it maybe is around 1,000 watts. And if you're just...
You have a big electric radiator.
Yeah.
It's usually about 1,000 watts.
Exactly, yeah. But it's per square meters. So think about then placing...
It's like having it everywhere. I mean, it's
if we for every square meter here would have one radiator in this room, then that's quite substantial. We would have, so what is this room? This is, I don't know, 10 times 10, 100 square meters. We would have 100 radiators in here, all on full effect. That's quite substantial. That's, yeah, excellent. Get a sense for this. Okay. Then the question was, okay, so this is if you look at 1 square meter here facing the Earth, or facing the sun, sort of. But if we want to look at, so not all parts of the Earth is exactly facing the sun the whole time, right? We up here in the north is apparent outside are not in the same position as the equator, being perpendicular to this radiation that comes in. So if we want to average, if we want to sort of have an average for the whole Earth for a whole year and so on, how do you get to that? And I'll go through it quickly, or the intuition behind it, and there's more about it in the book, how to think about this. But the idea is, okay, so this is the amount, the intensity of the solar radiation per square meter at the top of the atmosphere. Again, we can calculate the total energy that the sun receives, or the Earth receives. So what is the area of the Earth as seen sort of by the solar radiation? Well, the effective area is actually a circle, right? You can see that as if you would look at, if you would stand behind the sun and having the Earth blocking your vision, you see the shadow of the Earth, which is a circle, right? That's the area of the radiation that is sort of absorbed by the Earth. So what we can do is we take this, the solar constant. So, and then we multiply it by the area of the Earth, which is P R Earth part to 2. So then that's the total amount of radiation that sort of reaches the Earth, right? You okay with that? And then we spread it out over the total area of the Earth, which is 4 pi R2 Earth. And these cancel out. So we have divided by 4. So if we average all of the radiation that reaches sort of the effective area of the Earth seen from the sun over the total area of the Earth, then we have 1/4 of this. Does that make sense? So this is roughly 342 watts per square meters. So then you can go on based on that, do the same exercise we did yesterday with this bare rock model, and you can calculate the average temperature of the Earth if you have no atmosphere, and you'll arrive at about the same answer we got yesterday. But I thought I would go on to exercise number 2, where we have this slightly more complex model of the greenhouse effect. If you're fine with this. Okay, so this was the model. It's similar to the one we had yesterday. So now we have this. So we use the same thing we just did. So we have the solar constant divided by 4. That's the average solar insolation per square meter all over the Earth. Some of that gets reflected back into space, some of it from in the atmosphere, from clouds and so on, and some of it from like snow and ice on the surface. And the share is given by this alpha, something called albedo, and we'll talk more about that when we get to some of the feedback effects. Okay, that warms the Earth, that then radiates energy, infrared radiation. Some of that now we assume escapes directly out into space, while some of it gets absorbed in the atmospheric layer. So yesterday we assumed that everything was absorbed of this in the atmospheric layer. The atmosphere was, again, a perfect black body when it came to infrared radiation. So all of the incoming infrared radiation was absorbed. Now we assume that this is no longer a perfect black body. So some of the radiation actually passes through the atmosphere, straight out into space. What is absorbed is given by the emissivity of the atmospheric layer for the infrared radiation. So again, remember, emissivity equals absorptivity. So the atmospheric layer's ability to absorb this incoming radiation is given by its emissivity. Is that clear? So epsilon of this gets absorbed, and 1 minus epsilon is radiated out into space. And then this, of course, we have a temperature of the atmosphere. And the atmosphere then radiates also out into space, again, given by the same emissivity and governed by the temperature of the atmosphere. And some is radiated back down onto the Earth, right? So we can proceed as we did yesterday to write down the energy balances for the atmosphere, for the Earth, and for this system as a whole. So we can start with the energy balance of the surface. So what is the incoming energy that is absorbed by the Earth's surface in this model? E sun divided by 4. Epsilon at times sigma temperature of the atmosphere, part 4. So this is the downward radiation here. It's re-radiated, but the back radiation, as you call it. Yeah. Have we missed something here? 1 minus alpha. Yeah. So this is what is absorbed by the surface. Okay. And how much is radiated out into? Well, that is. We assume again that Earth is a perfect black body. So it's just sigma times temperature of the Earth, part 4. Right? So the energy balance for the atmosphere. So what is the energy that is absorbed by the atmospheric layer? Yes. So epsilon atmosphere times sigma times T Earth. Good. Part 4. So this is what is the share of this radiation that leaves Earth that is actually absorbed by the atmosphere, right? And what leaves the atmosphere? Well, it's 2 times epsilon atom times sigma times T atom, the part 4. because radiation goes both up into space and down back to Earth. So one of the tasks here was to calculate the temperature of the atmospheric layer. And that we can actually do just from this. Because we know what was given in this exercise was actually the temperature of the Earth. So you might recognize this from yesterday. We actually, E at and sigma cancels out. So we have that T at equals T Earth, divided by the 4th square root of 2. T Earth was 288 Kelvin, right? So the temperature of the atmosphere now is 242 Kelvin, or about minus 31 degrees. So how does this relate to or compare to the temperature of the atmosphere that in the model we calculated yesterday? Cooler, yeah. Why is it cooler, do you think? So yesterday we got a temperature of the atmospheric layer of about minus 20 degrees. But now we have something that is quite a bit cooler. Sorry? So what is the difference between this model here and the one we used yesterday? That's not really different. That doesn't make, that's just, it doesn't really matter, because that radiation doesn't interact. So we can skip that. That's just the same. It's just, yeah. Yeah, but so yesterday, well, what we did yesterday, we just said that this is 340 watts per square meter. But so the number we use here, which is 342, is more or less the same. Yeah, exactly. So the difference in this model compared to the one we used yesterday is some of this radiation actually passes through the atmosphere and goes straight out to space. So if we would assume that this is 1 here, so this would be 0, then we would have the same thing again. That's true. Yeah. So actually we can yeah. Now let's say, so why does this make a difference? Well, you can think about it like this. Remember again, or let's write down the energy balance for the whole system, right? So the total energy balance here. So what comes in is again 1 minus alpha I sun divided by 4. That is the energy that the total system receives, right? Earth as a whole. And what leaves the Earth here? Well, it's this. 1 minus epsilon at sigma T Earth power to 4. And then what the atmospheric layer radiates out. Right? So the difference in this model compared to what we saw yesterday is actually this part, right? This we said this is just the same, although we had 340 watts per square meter here instead of this I sun divided by 4. But it's the same amount of energy that the Earth receives, right? But now we have some of the energy actually comes directly from the surface. So this part here is actually, we didn't have in our simple model yesterday, right? So if we want to still have energy balance, so we still receive the same amount of energy. This is similar to what we had yesterday, but this is new. So if we still have the same energy input, same amount of energy that comes to the Earth from the sun, then the total here must be the same, right? Otherwise we don't have energy balance. So the same amount of energy must still be radiated out into space. If this would be more, then the temperature of the Earth would be going down. We would have cooling, as we said. So if we introduce this here, then we must actually reduce this, right? So we have the same amount of energy coming in. If we have some energy sort of escaping out here, then the atmosphere can no longer also radiate out the same amount of energy, because then we radiate out more than we actually receive. And how can that, what is necessary for that to happen? Well, the temperature of the atmosphere has to be cooler. Does that make sense? Yeah, the question is what? The question is the mechanism behind it increasing here. Because one reason for it to increase can be that the solar radiation goes up. Yeah. And then this doesn't have to. So okay, but if it's external, so let's say it's sort of chemical reactions in the interior of the Earth that causes the surface to, for example. But then again, we need to put something here. That external must be part of our energy balance. Okay. So we can't just change this and say, well, if we something must have caused that. And it could be a change in the incoming solar radiation. It can be, and which is what we're doing right now, is the change in this factor. Okay. That will actually cause the temperature increase here. So if not necessarily, because what happens, then you change two things here. You change the temperature of the Earth, but you also change this. So actually we already have that. We already have that, because what we did yesterday was increasing this to 1, right? And do you remember, so we know then that the temperature of the atmosphere was actually warmer. But the temperature of the Earth was also much warmer, because we had, well, you'll see. Because we haven't calculated the temperature of the Earth here. But yesterday we came to the conclusion that the temperature of the Earth here was, sorry, we already assumed that this is 288 degrees Kelvin, which is like 13 or 14 degrees Celsius. Whereas yesterday, when this was 1, the temperature of the Earth was 30 degrees. So you can't just change one of the sort of variables. It's a really good question. So you have to understand, okay, why did that happen, and how does that affect the other parts of the equation? Thomas.
Question. I'm wondering about, we have average temperature of Earth. But yeah. Earth is, some places on Earth are warmer. So I assume that there's more radiation from Nigeria than from Sweden.
Yeah, yeah.
And when you take averages of things and then raise them to power 4, it seems there would be a problem.
Yeah.
The average of a variable to the power 4 is not the same as the...
Yeah. That's a good question. Let me think about that over the break. Why you don't want professors in the audience while you're lecturing? No, it's a great question. I need to think about that. It's almost time for a break, so let's just do one thing. The other thing we're going to calculate was the emissivity of the atmosphere here. So if we plug in our T at the power to 4, or this relation here, we can rewrite the right-hand sign here as 1 minus E at sigma T Earth per to 4 plus E at T Earth per to 4 divided by 2. And let me do this quick and just, yeah, you can, it's just sort of tedious algebra. What we get here is 2 times sigma T Earth power to 4 minus. So if you put the numbers here in, you'll get that the emissivity of the atmosphere in this model is 0.773. So 77% of the outgoing infrared radiation here is captured, absorbed in the atmospheric layer, but the rest, so 23%, goes directly out into space.
And that's a number that's changing all the time.
Yes.
Is
So-
it like changing a lot? Is it going from 76 to 77?
So the next exercise you're going to do for tomorrow is actually changing this from 0.773 and increasing it by 0.019, which is quite a small change, but corresponds roughly to a doubling in this model, which is a simplification of the carbon dioxide concentration in the atmosphere. So you're going to actually look to see okay, if we change this model, increasing this, what is the effect of that on temperatures in the model? So what this says is that it says 2 things. You're right. So one thing it says is of the radiation that infrared radiation that the Earth radiates, the atmospheric layer absorbs about 77% of that. But it also says, that since it's not a perfect black body, it radiates less than a perfect black body would have done. So because for a perfect black body, this is 1, right? So a perfect black body radiates more than an imperfect black body. So it loses less energy. Yeah. So Stefan Boltzmann's law is that the intensity equals emissivity times sigma times temperature to the power of 4. So that is part of the Stefan Boltzmann's law. Yeah. So Stefan Boltzmann's law does not only apply to black bodies; it also applies to not perfect black bodies. But then you have to account for this emissivity factor. The constant is the same, exactly. Yeah. So how much an object will radiate, the energy it will radiate will depend on its emissivity and its temperature. Yeah.